So here we have a roller coaster of mass 3,100 kilogram, and it's released from rest at point A. Here's point A from the left of the diagram, and it says here part A, B, C, D, E. If you need to pause the video real quick, read up the different parts, and then keep up. All right. Other than that, I will get cracking. Part A asks you to find the speed at point B, assuming the system is frictionless or the track is frictionless. Okay. So we're gonna go from A to B. So to do this, I'm just gonna use conservation mechanical energy. Here, because the system is frictionless, I can do this. Mechanical energy initial at point A must equal to the mechanical energy final at point B. This is called a conserved system because there's no energy loss due to friction or anything like that that's stated. All right, so this one's pretty straightforward. But mechanical energy can be broken up for this diagram into potential energy plus kinetic energy, and that is equal to the potential energy plus the kinetic energy at point B. So really, you're doing A equals B. Okay, but here I notice in the diagram, or in the statement, excuse me, it says it is released at point A, or released from rest at point A. Because it is released from rest, I'm going to cancel out KEIA. The kinetic energy at point A is 0 because the object, or the roller coaster in this case, is not moving. And then if I look at point B as well, which is, well, drawn on the floor here, because point B is the lowest point and it's actually touching this horizontal line, which is indicated like on the floor, there's no height. Because there's no height, there's no PE. Okay, so keep in mind as you practice, KE only exists if the object's moving. For this one, at point A, the object is stationary, so there's no KE. PE only exists if the object is off the ground. You know, there's some height off the ground. But in this case, it's not off the ground, so the height is 0, so PE F at point B is 0. From here, we can just break up PE. The definition of PE is mgh. What's h? Well, just stick with your reference point. This one, you start at point A and you end at point B. So the height here would be at point A. And then KE is just 1/2 mv squared. Well, what v? V at point B. Okay, so the initial is at A, the final is at B. But if you notice here, mass cancels out on both sides. So as you practice these frictionless system, you notice that mass will cancel out because it's independent of mass. Okay. All right. To solve for VFB square, I'm going to go ahead and multiply both sides by 2. So really, I'm just going to move this 2 to the top left, or that's the same thing as multiplying by 2. So here I have 2 times G times H initial, or the initial height at point A, is equal to the final speed at point B. Okay. So we're going to go ahead and plug values in. To get VFB by itself, we're just going to square root both sides because there's an exponent square there. So to get rid of that, we just radical both sides. So now that we have this function, we can just go ahead and plug in G and HI being 140 meters in the diagram. So I'm just going to plug it in real quick. G is 9.8 meters second square, and then H is 140. Now, in case you're confused why this is positive 9.8, the function here is 1/2 mv squared, but v being the speed, not velocity. So because you can't take the square root of a negative number. Now, I mean, unless you want to, you could put negative 9.8, and you can also put negative 140 because it's technically, you know, descending. But at the end of the day, keep in mind that the v here stands for speed, not velocity. So really, you can leave the negative signs out. Okay. All right. Other than that, 2 times 9.8 times 140 is 2,744, and then the square root of that will give us about 52.4 meters per second. So why this says VFB, this is just the final speed, because the question here at the very top of the screen in part A says what is the speed. So I don't need to include the direction, so the speed is 52.4 meters per second. All right, that is part A. Part B asks us to find what is the speed of the roller coaster at point B. Once again, pay attention to the wording. It says here this word is speed. So speed is a scalar, so I don't need to provide any sort of direction. At point C, which is at the peak here in the second hump, or excuse me, I guess you can call it second hump. So point C here is 95 meters above the floor. So we can use the same strategy. You just have to be careful when you can and cannot cancel things out. So here, I'm going to go from A to C. You could go from B to C, but I'm just going to go ahead and be consistent and just go from A to C. All right. Well, at point A, I can expand my mechanical energy out into PEIA again plus KEIA. And then here, my final location, though, is at point C, which is PEFC plus KEFC. But once again, if I'm starting at point A, KEI at location A is 0 because the system starts at rest. the only energy that exists is the potential energy due to gravity at point A, because there is a height involved. Now, if you look at point B, excuse me, point C though, right? Point C is 95 meters off the ground, so you cannot cancel PE out like I did in part A. So always kind of go with the flow. Each diagram is a little different. Each part of the problem is a little different. Here, the only thing I can cancel out is KEIA because it is the only thing that is zero. So don't memorize stuff. To expand PE initial at location A, once again, it's just MGHIA, just like the left side of the working part A. But here, PE final at location C is MGHF at location C, which is 95 meters, and then 1/2 mv square, v being the final speed at point C. But once again, you notice mass cancels out, so keep this concept in mind. Okay. Other than that, though, we can just reduce this function down. All I do is I took out all the m's because they all m appears in every single term, so that's proper to do. I can cancel it out. To solve for the VFC square, the first thing I want to do is I want to move this positive GHFC to the left side. So therefore, I have the GHI at location A minus GHF at location C. That equals the 1/2 V final at location C square. Well, I want to do a couple of steps in one here, okay? One, both of these terms on the left has a G in common, so I'm going to factor out the G. Hence, the G is in the front of the parentheses here. Now, how come there's a 2 there? Well, I'm going to multiply both sides by 2. Hence, there's a 2 there. So hopefully your algebra is good that you just kept up there. I did 2 steps in one. I factored out with G on the left, and then I multiply both sides by 2 because I need to get V final at location C squared by itself. Alright, if you kept up with that, the rest should be plug and chug. Well, G is 9.8, HI is 140, HF here at point C is 95 meters off the ground. And if you plug all this in on the left side, your calculator should output about 2,557.8. But you notice here this is VF at location C square, so we need to get VF, so we need to take the square root of both sides. So the square root of 2,557.8 will give you about 29.7. Okay, so that is your final speed at point C. So by the time the roller coaster gets to point C, that is how fast it's moving. All right, let's go ahead and crack out part C. Part C says, assume again that friction is negligible. What is the speed of the roller coaster at point D? This one is pretty light work, so pretty much the same three parts. The first three parts is kind of the same process. I want to highlight this function here because I've already derived this function. This function is pretty solid for any given 2 locations. So except this one goes from A to D. So I carried that over the 2, which is here, the G, which is a constant. But you notice here the only difference here is that my final location is at location D. So therefore HIA is the same. HF is now at location D because that's what part C is asking for. And the final velocity or the final speed at part D. Okay. So I'm just using the same function I have here. So instead of writing all my work over again, I just carry it over. I'm going to just apply it. Well, 2 stays the same. G is 9.8. Here, HIA is 140 because at location A is 140 meters off the ground. At HF, at D, well, if you look at the diagram, D is 80 meters above the ground. So therefore, if you take there, 2 times 9.8 times, 60 meters, you'll get about 1,176, and that is VFD square. Once again, this is VFD square, but to get VFD by itself, we take the square root of both sides. So if you take the square root of 1176, you'll get about 33.4 meters per second. So that is the speed at point D. Okay. All right. Now let's do D and E. Part D asks you to find. It says assume that the segment from point D to E is the same height above the ground, aka 80 meters. So from D to E is the same height. Find the time to cover 120 meters. Well, I think the quickest and easiest way to do it is just using the average speed function. You can use this function because I know that once the roller coaster gets to point D, it stays at the same height, and because it's frictionless, the roller coaster is not going to speed up nor slow down. So it's moving at a constant rate. Because it's moving at a constant rate, I can use the average speed function. Okay, so you have to make sure you apply physics correctly here. I'm using this because I know it's frictionless, and because it's frictionless, it's not speeding up nor slowing down, so it's moving at a constant velocity. All right, other than that, to solve for T, I'm just going to multiply both sides by T, divide both sides by S average, or just switch S average and T. Move the T up, move the S average down. Here, we know the distance already. The distance in the problem is given as 120 meters. And then S average We just found that the speed at point D, okay, from our previous part C is 33.4, but it's not speeding up or slowing down to part E, so therefore it maintains the same 33.4 meters per second throughout D to E. So I'm just going to use that speed that I just found. Therefore, if you do this correctly on your calculator, you should get about 3.6 seconds. So it took about 3.6 seconds to go from D to E, okay, under that rate of 33.4 meters per second, which makes sense. Excuse me. Now, part E, I think is a bit more challenging. Part E here says, now suppose that from A to B, friction does some work on the roller coaster. Excuse me. Equaling negative 5.3 times 10 to the fifth joules. So you notice here the negative sign, right? It's just now all of a sudden work due to friction is present. Okay. So well, when friction is present, energy, mechanical energy is taken away from the system. It goes into other forms of energy, such as heat, vibration, whatever it is. Now the question is, will the roller coaster make it over the slope to point C? So from A to B, it's going to lose some energy. The question is, will it make it all the way up to point C? Well, how do you figure that out? Easy, run a test. Okay. Here, you notice my starting point is a little different. Instead of saying mechanical energy initial at point A is equal to mechanical energy at point B, as I did in the previous parts, here I took the initial energy in the system. I'm going to subtract it from the work that's lost because it said so in part E, right? So part E is no longer frictionless. There's friction. Well, the work due to friction is negative because it's acting against the roller coaster. So here, this is for a non-conservative system. Non-conservative just meaning there's now friction involved. Well, mechanical energy is measurement in joules. Work due to friction is measured in joules. So therefore, we can just take the mechanical energy, subtract it from the work due to friction. That gives us how much is left over at point B. Okay, so the mechanical energy, once again, at point A can be broken into two terms, PEIA plus KEIA. And here, instead of saying work due to friction, I'm just going to convert it to energy loss. So work due to friction is the same as energy loss. Sometimes folks like to use the phrase energy loss, quote unquote, because it's taken away from the mechanical energy system. And then MEF at location B is simply PFB plus KFB. But if you kept up with the beginning of the video, we can cancel a couple things. KEI at point A is 0, and then PEF at point B is 0 because there's no height involved. Okay, so really we can clean this up a little bit, right? PE is just MGH, and then E loss is just given to us as negative 5.3 times 10 to the fifth joules. And then here, you notice I didn't break up KEFB, right? So again, you have to kind of go with the flow. You can't just sit here and memorize stuff and then, break it up into 1/2 MVFB squared. Here, I kept this term on the right as is. It's just KEFB because what I can do is I can run a test. So if I plug in values MGHA, so if I plugged in 3,100 kilogram times 9.8 times the initial height at point A, which is 140 meters in the diagram, I'll get this big number, 4.2532 times 10 to the 6 joules. And I kept it in scientific notation here because the work due to friction is given in scientific notation. So the work due to friction or energy loss is given as negative 5.3 times 10 to the fifth joules. That's what I replace it with. Okay. Once again, I'm already telling you that it's negative, so please don't undo the negative sign by plugging another negative. Otherwise, you're saying you're adding energy to the system, right? So here we're subtracting the energy that's lost. And that should give us how much energy is left at point B. It's like spending money. It's how much you have, it's how much you spend, how much do you come home with. That's all. All right. So if you punch 4.2532 times 10 to the 6 minus 5.3 times 10 to the fifth in your calculator, you'll get about 3.7232 times 10 to the 6 joules. So that's how much kinetic energy you have left at point B, right? So you start off with this much, you lost this much, this is how much you have left. And all of that is in the form of kinetic energy at point B because there's no height involved at point B. So all of the energy goes into kinetic. Well, how do I know if it can make it up to point C? Well, I can just figure out how much energy is at point C, right? If the roller coaster goes all the way up, and assuming it stops at point C, well, all of that energy is going to go into point C. Okay, all the kinetic energy is going to go into C. So how much of that energy? I can just run a test real quick. Well, I can figure out how much potential and energy is at location C. Well, here, the potential energy at location C is simply mass times gravity times the height at point C. Well, mass is given, G is 9.8, the height at point C is 95. So if you plug all this in your calculator, you'll get 2.8861 times 10 to the 6 joules. Well, this is how much you need in order for you to get over the hump at C, right? But at point B, you have more than B. Or excuse, at point B, you have more than what you need at C. So by the time you get to point B, you have this much energy, 3.7232 times 10 to the 6 joules. But this is all you need to get over the hump at point C. You only need 2.8861 times 10 to the 6. Well, 2.8861 times 10 to the 6 joules is less than what you have. So you're going to make it over the hump. Okay. So I would like to say that the kinetic energy exceeds what you need in order to get over the hump. All right. So other than that, the answer for part E would be yes, it will make it over the slope at point C, because the kinetic energy you have at point B exceeds the potential energy that's needed at point C. All right. Other than that, I hope that helps. Stay nerdy. Don't be whack.